Hey guys, it's MedHead, and today we're going to start our OChem series. This video can also be helpful for Gen Chem and also Biochem, but it's a good foundation for you to start with when you start with mechanisms. Enthalpy is really important when you think about the reactivity of a mechanism, but you also want to take into account entropy, Gibbs free energy, kinematics, those kind of things, and those will be in later videos. I'll get those out to you, and let me know if you guys want to see other videos that I kind of haven't put out over OChem, and I'll be happy to work on those for you guys. So let's get started. Alright, so today we're going to be talking about enthalpy. Enthalpy is one of the components that help determine whether or not a reaction is likely to happen. So, when we think about enthalpy, keep in mind that there's also entropy that helps determine overall whether or not a reaction will occur, but that'll be happening in a later video. So today, let's look at enthalpy. Enthalpy is right next to this flame, so basically, let's say that enthalpy is heat. Enthalpy is also represented by delta H. You'll see it written as this, and it basically is saying there's a change in heat, H meaning heat. With that in mind, when we think about enthalpy being heat, let's think about, okay, so what is heat? Heat is formed by the kinetic energy of molecules. So basically think about delta H as a type of energy. In a reaction, there's a lot of making bonds and breaking bonds. When you make a bond, you release energy, which means you're going to have a negative delta H because you release that heat or energy. When you're getting married, think about it, you're making a bond and you're releasing a lot of stress, a lot of cares, so you're going to have a negative delta H because you released energy. When you're breaking a bond, you need energy, which means a plus delta H, you need that energy or heat. Think about getting a divorce. You're breaking that bond. You need a lot of energy. There's a lot of stress that goes in a divorce, so you need that positive delta H or energy to break that bond. Whenever you have a stronger bond being made, you release a lot more energy. It's kind of like when a relationship between a couple is stronger, you're releasing a lot more stress when you get married. Whenever you have a lot stronger of a bond being broken, you need a lot more energy to break that bond. It's kind of like a couple who are really close to each other. It's going to be harder to get them divorced. So there's going to be a lot more energy in that. So, when we think about getting a divorce, let's think about breaking that bond. We're going to think about two different types of ways to break a bond. Those two types of ways to break a bond are called homolytic and heterolytic cleavage. When we think about homolytic, think about homo means same, so they're sharing those electrons when they are broken. So here we have X and Y, and we're going to represent it by single-headed arrows because they're sharing equally those two electrons. Each one's going to get one electron. So here we can draw X with one electron and Y with one electron. Because they are radicals, which means they have unpaired electrons, that means they're uncharged and they're going to be a result of the homolytic cleavage and sharing those electrons. So they both get their own, and they're not really going to be any type of charge because they each got one electron, making it a radical. With heterolytic cleavage, there is going to be an uneven sharing of electrons when the bond is broken. That uneven sharing of electrons is going to be represented by a double-headed arrow. Let's say Y gets both of those electrons. Y is a little more selfish here. They're going to take those electrons. Because X is not getting any of those electrons, he's going to be without them, and he's going to be positive. These two electrons came over here by Y, and since he got both of them, he becomes negative. This created ions, which means there was an uneven sharing of electrons, and now there's going to be charged molecules after heterolytic cleavage. So let's rewind back to homolytic bond cleavage. When we think about how much energy it takes to break a bond, we think about delta H naught, which is basically like enthalpy, but it's specifically for how much energy it takes to break homolytic types of bond cleavages. How much energy it takes for the homolytic process to happen. So often you'll see delta H naught written as BDE, which stands for bond dissociation energy. The units are often given in kilojoules per mole or kilocalories per mole. A lot of the times they'll give you in kilojoules per mole, but sometimes you'll see this. So this formula down here is provided for the overall reaction delta H naught. That's what the RXN stands for. So this delta H broken minus delta H formed means you must take all of the bonds that are broken and its bond dissociation energy minus the bond dissociation energy of all all of them formed. But you might be like, why do we use bond dissociation energy if they're being formed? Well, if we come up here, we can see that negative delta H means that the reaction was exothermic. That means that there was a bond being formed. So, to indicate that a bond is being formed or an exothermic process is occurring, use negative delta H for the bond dissociation energy. For the bond dissociation energy for bond being broken, use the positive because you are required energy. You need energy to get that divorce. You need energy to break those bonds. So that is why you have positive and then a minus. So let's do an example. So here in this example, we have a reaction that occurs between an alkane and a dichloride, and we're asked to give the delta H of the reaction. So when we look at it, we're given all of the bond dissociation energies in kilojoules per mole, and when we assess what's happening in this reaction, we have to look at all the bonds being broken and all the bonds being formed. So here, let's look at it, okay? So we know that there's some ghost hydrogens here. We didn't write them because they're not always necessary, but here it's necessary because we have a Cl replacing one of those hydrogens here. We see that a bond is being formed between the Cl and this area, and we see that to form that bond we have to take this H off, which means we're breaking a bond of H from a CH. So that bond dissociation is 397. So if we come down here, or let's write it up here, and write delta H equals 397. 397 is of this being broken. But to attach one Cl over here, to get that, don't we also need to break a bond here? Yeah, so let's break Cl. We know that the bond association energy for Cl, and up here we chose positive because it's being broken, correct? So we need a positive delta H. Here it's also being broken, so we need a positive delta H plus 243. Now, we can look at all the bonds being formed. Here we have a Cl being attached to replace that H, and we know that a Cl attaching to a CH has a bond dissociation energy of a negative 335. It's negative because, what are we doing? We're forming a bond, so it's negative. It's a release of energy, release of heat. So we can do 335. We also know that Cl is attaching to the H that was taken off here to form this, and we know it's 431. They're forming a bond, so we know this negative can distribute over here also. And then we'll have initially 640 minus 766. So if we look at 640 minus 766, is that going to be a positive or negative number? It's going to be a negative number, and we're going to have, let me erase this here so I have space. So we're going to have negative 126 kilojoules per mole, and that's our answer. So if we look at it and we're like, oh, okay, that's our answer, and we have a negative delta H, what does that tell us? That tells us we had an exothermic reaction. There was a release of heat overall. Overall, we have a negative delta H exothermic reaction. That's how you would do those problems. Generally, the release of heat is usually favored, but like I said earlier in the video, entropy also plays a part in determining overall whether or not that reaction is favorable, and I'll be going over that in the next video. Alright guys, leave a like if you guys found this video helpful. Let me know if you want more information or other topics that you want me to upload. Like I said earlier, leave comments, questions. I'll be really happy to answer them. The next video should be over entropy, so be on the lookout for that. And I'll start the reaction series later. I thank you guys for watching this video, and this has been another episode of MedHead. See you later.